Hello everyone, welcome to the channel. This is now we are solving question number 15 of NEST 2025 exam. So the question says the Parker solar probe orbiting the sun experience solar radiation flux of 650 kilowatt meter square. So it says solar radiation flux, that is the intensity of the solar rays incidenting on the Parker solar probe, that is energy per unit area per unit time. This is given as 650 kilowatt per meter square. The heat shield the heat shield has an area of heat shield is given as 1 meter square and emissivity is given as 1 surrounding the probe. The heat shield is surrounding the probe is internally cooled by a conductive heat transfer mechanism. The shield is designed to operate at 1500 Kelvin. So the shield temperature is generally around 1500 Kelvin, and the required heat transfer rate we have to find it. What is the heat transfer rate? So we know that, let's say we have the sun and it is emitting radiation, and we have the Parker solar probe, let's say some distance behind it. Let's say this is our Parker solar probe. Okay, so the uh, temperature, the heat that it obtains is equal to the radiation incidenting on it. The radiation that will incident on it, radiation incident, will be either absorbed or reflected by the Parker solar probe. Now, some part of the radiation is absorbed and some part will be reflected. The part that is absorbed is that part that we have to cool by applying the coolant, or we have to by applying the coolant we have to cool this part. So we have to find what amount of heat is absorbed. Incidenting radiation, we know it's 650 kilowatt per meter square. Reflected, what is reflected, we have to calculate this by black body radiation, assuming this as the black body and its emissivity is equal to 1. So how much radiation it can emit, by that we can get the reflected part or radiated part. Okay, so for that we can use the formula of Stephen's Pools. This is the Stephen's constants, and then it is the heat that is reflected is equal to sigma a t raised to power 4. Okay, so by this formula we can calculate the amount of heat that is reflected or radiated by this Parker solar probe. So for that, now next part is, let's calculate the absorbed. How much amount is absorbed? It is equal to radiation that is incidented minus the reflected part or the radiated part. So the incident radiation is 650 kilowatt per meter square, and for the reflected it is, what is the value of sigma? It's constant, that is 5.67 into 10 raised to power minus 8 into the area, that is equal to 1, and the temperature of the Parker solar probe, that is 1500 raised to power 4. Okay, so now when we solved it, we will get its value as its value coming out as somewhat around 2.87 into 10 raised to power 5 watts. This is in kilowatt per meter square, and this is in 287 287 0.06 kilowatt. Okay, so now this is in kilowatt per meter square and this is in kilowatt. How come? So first of all, this is in kilowatt per meter square because it is the total amount of energy or heat incident on it per unit area. What is the area of the total heat shield? It is 1. So the total amount of radiation incident is equal to 650 kilowatt, not kilowatt per meter square, minus on the complete area total the heat that is reflected. This is the amount of heat reflected. So absorbed heat is equal to, it's something equals to 362. On solving this we get 362.94 kilowatt. So now from inside, from the coolant, we have to provide this much amount of heat for its maintenance. The heat transfer must be equal to this for maintaining it. Okay, so this is close to this option A. So option A will be the correct answer. Hope you have understood the solution. Thank you for watching.